The Physics of Color, Colored Light, Part 2. One of the most often asked questions in all of life is, why is the sky blue? And the most common wrong answer is that it reflects the ocean. That's not why the sky is blue. We'll talk in a few minutes about why ocean or the lakes, water is blue. But for now, why is the sky blue? Well, light, let's take the 7 colors, Roy G. Biv, and take the 3 primaries out of that. We'll take the 3 primary colors like we talked about last time, red, green, and blue, but we can talk about all 7 if we wanted to. And this diagram here on the left, the green part there is supposed to be the Earth, and the blue shaded part is the atmosphere, which to scale is not that thick. It's a very thin shell of atmosphere, but just for effect here. You have a person standing on the Earth getting hit by light. This is supposed to be a person. Some of that light goes into your eyes, and you're usually not looking directly at the sun, but you're looking at things around you because light reflects off of those things into your eyes. And once again, may I stress, the color that we see, the color that goes into our eyes is the color we perceive the thing that we're looking at to be. So if you have a blue shirt, it's blue because light is hitting that shirt, at least blue light is hitting that shirt, bouncing off that shirt into your eyes. Things look the color that they reflect into your eyes. So the atmosphere at the base level is blue because, or the sky is blue because blue light is coming from that area into your eyes. And the source of that light is from the sun, but what happens is most of the colors pass straight through the atmosphere very efficiently, but blue, at least part of it, not a large part, gets scattered. Go back to the top here. In other words, as the blue light, part of the spectrum of visible light coming from the sun, goes through the atmosphere, not all of it goes straight through it. It hits an atmospheric particle, the oxygen and nitrogen, which is the predominant particles, elements in our atmosphere, like over 90% oxygen and nitrogen. The blue light tends to interact and starts bouncing all over the place. So, but a lot of it comes straight through still, so the things around you can still see as blue because there's a lot of light still coming through. But for example, if this diagram I have here on the left, and I draw, say, another person over here, and say it's in a different city next to where you live, all right, that person is getting blue light that was originally going towards you, but now it's coming towards that person. So when that person looks up, there might be some blue light goes into their eyes, and that person says, oh, I see blue coming from that direction, even though the sun is directly overhead. Blue light coming from that direction, so it looks like there's blue over there above that other city. So they see blue sky. Likewise, the second person I just drew, there's light, Roy G. Biv, going towards that person, but some of the light, some of the blue light that was going towards that person, the red and the green tend to go straight towards them and hit things around them, but some of that blue light, not all of it, but a small portion of it, scatters or reflects, basically bounces off atmospheric particles, and some of that blue light meant for them goes to my eye. And I look that direction over that city and I see blue coming from that part of the sky. The sun is not right there. I have to look in this direction to see the sun. All right? But if I look over top of that second person, I see blue light coming into my eyes. Once again, you don't see light that's leaving you. You see light coming into your eye, and that's what you perceive as the color of the thing you're looking at. In this case, the sky, which is above you in different directions. And once again, if I go back to the first person, there's also blue light that's coming down this way into the atmosphere, hitting particles and going to your eye. If it's a sunny day and it hits into your eyes from all over the place, so you see blue above you, straight above you, and to the cities to the left and north and south, east and west of you. Now, sunsets. Sunsets are red basically for the same reason. And a lot of this has to do with the geometry of the atmosphere and the low angle at which the sun's rays come in at nighttime. So once again, a not-to-scale diagram over here on the right-hand side. At sunset, this is supposed to be a person at sunset, getting dark. The little red arrows show the red light getting through the atmosphere all the way to the person. Let me kind of go over top of this. Going to the person's eye. Whereas the blue light, when you have a longer path, because when you come in at an angle, like tangentially to the Earth at sunset, the blue light is going to be passing through a longer layer, basically, because of the angle of approach to the Earth through the atmosphere. More of it gets taken away, and the more blue light you take out of the Roy G. Biv, the more reddish the light's going to look. So you'll see red light, more red light coming into your eyes, and therefore the sunset is orangish red. Well, let me back up for a second here. I forgot one thing on the left here. Dry, clean air will be the bluest of all air or atmosphere. When you put moisture into the air, humidity, obviously when you put clouds, which has a massive amount of humidity, water in the air, water vapor, it becomes white, because white clouds basically are scattering all types of colors, red, orange, yellow, green, blue, indigo, and violet to your eyes, so it looks a whitish color. And the more and more water the clouds contain, the more they absorb and don't even reflect, they become darker. So we know those are rain clouds because they're absorbing light, they're dark. But going back to dry air, if you don't have much water vapor in the air, the blue light is the only light that's going to be scattered. The other colors are not going to be scattered. When you start putting water vapor and dust particles and other pollutants, so to speak, into the air, some of the other colors get scattered along with the blue, and the more scattering that occurs from the other colors, the more whitish the sky is going to look. Not a deep dark blue when only the blue gets. So when all you have are the small nitrogen and oxygen particles in the air, the blue is the only thing that gets effectively scattered, and the sky looks a nice, deep, rich blue. Why is water blue? It's blue for a different reason than why the atmosphere or the sky is blue. Water absorbs the other colors other than blue more efficiently and quickly than red. For example, a small amount of water will look transparent or clear, but if you have a deep amount of water, like in a lake or an ocean, what happens is that the sunlight penetrates into the water, starts reflecting a little bit, but mostly it's going to be absorbed. In the red light, it's absorbed very quickly. In fact, I'm told that if you keep going straight down, red gets absorbed after about 50 feet. There's no more red light. But blue light can penetrate deeper in any color of light, whether it's red, orange, yellow, green, blue, indigo, violet. And according to this chart that you see above here, this middle bar right here is blue. It's showing you how far blue can penetrate. Essentially, however, there's not much blue that can get past 200 feet, which is only like 60 or 70 meters. But a little bit will go further. I mean, it weakens with the distance. It doesn't just all of a sudden goes to 280 feet and then it's gone, but it just gets dimmer and dimmer and dimmer and dimmer and dimmer and dimmer and dimmer. For all practical purposes, after about 200 feet or so, it's so dark you wouldn't be able to see if you were down there. You would need an underwater flashlight. But so the light penetrates and the blue sticks around longer. Some of it gets reflected back into the atmosphere, bounces off some particle, the water particle, and bounces back up into the sky, into your eyes if you're sitting above the water looking down. So that's why water is blue. So what is a spectroscope, you may ask? Well, you probably used them in chemistry last year. In fact, I know you did, but we're going to use them in class if we haven't already. It's an instrument that's used to determine the type of light given off by a luminous body. Usually we're looking at the colors, and there, I'll circle this here, with increasing wavelength to the right here. Red is the increasing wavelength. But here's a couple of spectrums. The top one is a continuous spectrum that might be given off, as you'll see in class, by like a light bulb with a filament, with a solid filament, where you're giving off a bunch of colors that are all mixed together, and they kind of blur. You're not seeing distinct lines like you are with the bottom diagram here, the line spectrum with this blue and two greens and two yellows and a red. I'm not sure what element that is. Each element, if you take a gaseous substance and you cause it to glow, every particular element will give off a pattern, a fingerprint, so to speak, for that element. And I'm not sure what element this is, but that's that particular element. Say it was carbon. I don't think it is, but if it was carbon, carbon will always give off this pattern because of the way the electrons jump up and down. Actually, as they jump down, they give off the line spectrum, the photons of light that give rise to these lines. So these line spectrums are really produced by gaseous substances that are glowing, I should say, when you pass electricity through them. So this bottom picture here, though, is the picture of the actual electroscopes or spectroscopes, the spectroscopes that we'll be using in class to look for these patterns in various light sources like incandescent, fluorescent bulbs, and other glowing tubes of gas. Here's an example problem or an application for spectroscopes or spectroscopy. When they look at, say, stars or elements that you burn or cause them to glow and they give off light, they give off a pattern. And you can tell what elements are present because we know every element's pattern. Here we have generic elements D, E, and G. Those are the patterns given off by those elements. It might be, carbon and oxygen and nitrogen. Who knows what these three elements are here? But if you have a mixture of some gas that you burn and you cause it to give off light, and you look at the spectral lines through a spectroscope and see what patterns given off, you can tell what elements are in that particular sample. So, for example, here, what elements are in this particular sample? Which, you look above and see which ones line up. And you can see that element G right above this mixture does not match up with any of the lines in the mixture. So element G is not part of the solution. That's not present in the sample that's being viewed right now. However, if you look at element D and you go straight down, all right, you can see how those lines are lining up, so to speak, with that pattern. So the mixture that we're viewing right now does have element E in it. So let's also check element D, and if you match them up, there is a correspondence once again. The lines from element D are present in the mixture, so the mixture contains both E and D. Answer number 1. So that's spectroscopy, seeing what elements are present in a mixture or a sample based on the line spectrum that's given off by that sample.